Is it built into Mac or?
Test, test, testing, test, testing, test, test,
Hello? I heard that. Yeah. You hear me? Yeah, that's move the mic. All right. Hello, everyone. Can everyone hear me okay? All right. Thank you so much for being here today. Even though it is cloudy and the weather's not very good, this is unfortunately what spring is like. We have 2 more public lectures that I'll talk about for the rest of the semester. So hopefully one of them will bring us good weather. But no matter what, we have a really fun talk for you all today. And so we'll get started with some trivia as always, then we'll do announcements, and then we'll hear from our speaker and do Q&A. So we'll start with trivia. We're gonna have 6 questions tonight. And the way this works is I will let you think about a question. Collaboration is encouraged. Talk with people around you. And then we'll vote. So I'll say 1, 2, 3, vote. And you'll show me 1 for A, 2 for B, 3 for C, 4 for D. So just to get a consensus of answers. All right, our first question. Where was this photo taken? Okay, let's vote. 3, 2, 1, vote. Show me your answers. I see 2, I see 3, I see 1. I don't think I see any D's or E's. All right, and it is C. This is the Peak National Observatory, and it is located in Arizona. Question 2. In addition to constructing ground-based and space-based observatories, telescope alone. Okay, let's vote. 3, 2, 1, vote. I see 1s, 4s, 2s. Maybe no 3s. And the correct answer is 1957. So it's been around for a while, but not as long as the telescope has been. It is cheaper and easier to make a balloon and launch your instrument than it is to put it into space. A lot of these balloons are launched in Antarctica because there's a specific wind pattern that lets the balloon kind of hover. But Antarctica has really bad weather for most of the year, so you have a really narrow window for when you can launch these balloons. All right, question number 3. One of the world's largest single pieces of glass ever made is inside of a telescope. The Hale telescope at Palomar Observatory has a 200-inch, 5.1-meter diameter mirror. How long did it take to grind and polish the mirror? All right, 3, 2, 1, vote. I'm seeing 2s, I'm seeing 3s, 5s. I think that's all I see, 4s. And it is 13 years. That's a very long time. I started to build my own telescope when I was, I think, 17, a very small one. I did not finish polishing the mirror. I gave up pretty fast because it takes a very long time. It is a very meticulous process. And when it's so much bigger, it will take a very long time. All right, question 4. A telescope that uses lenses, not mirrors, is called a... 3, 2, 1, vote. All right, you all knew this one. A refractor. And so even though you just learned that it took 13 years to polish that mirror, modern day telescopes more often use mirrors than lenses because lenses are even heavier than mirrors are. So how we build really large telescopes now that don't take 13 years of polishing, we make mirror segments. So instead of having one piece of glass, we break it up a little bit. Okay, question 5. With 3,200 megapixels, the Vera Rubin Observatory's LSST camera is the largest digital camera ever built. About how much does the camera weigh? Are we ready? This one takes some mental math, some calculation, because I know we all use these units all the time in our daily lives. All right, 3, 2, 1, vote. All right, I'm seeing lots of 1s, 5s, 4s, 2s. Box turtles. So this is a very large digital camera, much bigger than the one you have in your pocket in your phone. You would not want to carry around 3,000 box turtles. Pupin, this building has a name. What is it? 3, 2, 1, vote. Okay, I see 1s, 4s, 2s, 5s. All right, it is the Rutherford Observatory. I also did not know that until fairly recently, more recently than I would care to admit. So unfortunately, we won't be getting up into that dome today because it's too cloudy. Astronomers hate the cloud. If we had a superpower, we would get rid of the atmosphere. It would be very bad for us breathing, but the night sky would be much better to see. But hopefully in our next two lectures of the semester, we will have clear skies and the ability to observe. We will then have talks over the summer as well. So these are not our last two talks ever, but our next one is April 10th. And then our last one of the semester is May 1st. And then we will announce the summer schedule sometime at the end of May. And until then, we right now have a wonderful speaker. She's a PhD candidate. I'm going to hand it over to Meghna Shutaram, who's going to talk about developing telescopes. So please give a big round of applause to Meghna.
Hi, everyone. I'm Meghna. I'm really excited to tell you guys about astronomical instrumentation today. It sounds like a lot of syllables, but it's really just making the things that we use to observe space. And it's what I've spent the last few years doing. So I'm very excited about it. And I wanted to show you guys my title slide because this is at MDM Observatory, which is where I've done most of my observing as a PhD student, and it's a beautiful place. That's all. So I'll start off just by saying that astronomical instrumentation is a huge field, and what we'll focus on today is basically things that we use to observe light. And I just wanted to show you guys that that's not all that instrumentation is. And there are many other things that we receive from the universe. So there are other people that use things like neutrinos and gravitational waves to learn about space. So there's a little picture of a neutrino detector up there and the LIGO gravitational wave detector in Louisiana. And yeah, I just wanted to call attention to these other ways of observing the universe. But the one that I'm going to focus on is looking at light. And there's lots of different types of light and ways to look at it. And kind of the very first thing to know about it is something that you guys already kind of know because you, I assume, see color in your life. And the different colors are different wavelengths of light. So the longer wavelengths are redder colors and the shorter wavelengths are bluer or purpler. And these really affect the types of instruments that we build. So instruments can look completely different whether they're supposed to look at redder light or bluer light. And this becomes especially true once you start thinking about light that's beyond our visible range. So the same way that your dog or cat might sometimes hear things that are above your hearing range, we can build instruments that can see things beyond our visible range. And we're going to get into the ones that I've built, which is more of a specific type, but there's a huge range of instrumentation out there. It can look very different. So I just wanted to show you guys the difference between waves and bluer light, such as ultraviolet. So, of course, I had to include James Webb. We've been getting beautiful images from James Webb Space Telescope in the last few years. This is in space capturing infrared and near-infrared light. And yeah, this is one of my favorite images, the deep field, showing so many different galaxies. And another similar telescope in that it's in space, but completely different in that it's observing X-rays. So we're going from wavelengths longer than the reddest light that we can see to much shorter than the bluest light that we can see. So Chandra X-ray Observatory, also in space, has to be in space because our atmosphere will absorb X-ray light. So if we want to see anything from beyond our atmosphere, we have to go above it. And this beautiful image is the center of the Milky Way galaxy. Yeah, so not very similar looking to JWST. It doesn't have that huge segmented mirror, I think is the main difference that you might notice. And it's because X-ray observatories have to be built very differently from infrared ones. A large millimeter sub-millimeter array observatory. We all call it ALMA. But this one also looks extremely different. You might notice huge radio telescopes, and there are multiple of them. So can't do that in space. It's very difficult to send 10 telescopes into space. So yeah, keep this in mind. And the next one and the last one of the ground observatories is Rubin. This one also kind of just started up and shows we do not have multiple of them because that technique is not as useful for optical astronomy, more useful for radio. So these are some of the different types of telescopes that we can build. And I also wanted to talk about different information that you can get from light, because before this, I was showing you guys a lot of just pictures, but actually light can include other types of information, such as the polarization. So the polarization can be used to look at the magnetic fields in galaxies. We're not going to talk much more about this, but I just wanted to include it as another thing that we can use light to learn about and that we use quite often in astronomy. Okay, finally, we also can look at light across different wavelengths, and this is called a spectrum of light. And this is a spectrum of our sun. And you can see it gives off light at a bunch of different wavelengths, going all the way from purple to red. And you might also see that there are these dips in the spectrum, and those are from different elements or molecules in the sun that absorb light at a specific wavelength. So it's kind of like a chemical fingerprint that we can use to tell what molecules are there. And I also, this spectrum of light was taken with that weird looking telescope there on the right. It's the McMath Pierce Solar Telescope in Arizona. It's actually one of my favorite ones because one thing that you guys probably all know about the sun is that it's very bright. So that's why they had to make a super long focal length. So they had to make a super long tube for the optics so that they wouldn't concentrate the light and burn and deform the optics. So that's why it has this fun shape. And telescopes can also look like that. So I wanted to talk about spectroscopy today because that's what I've been working on. And first, I wanted to show you guys a little about how you make a spectrograph so that when you go home, you can all make your own spectrograph. And then I'll show you guys the ones that I've worked on to inspire some ideas for when you make your spectrograph. But the first thing is a spectrograph, sadly, cannot be the whole thing. You need a telescope first. It's kind of like the telescope collects the light and then you have to use the spectrograph afterward to analyze the light that you've collected. So this is a picture of a reflecting telescope, kind of like we mentioned during trivia. And that is the first component that you need in order to collect a spectrum. The second thing is the actual spectrograph, and that needs to have three components. No matter what wavelength you're looking at or anything, you need to have these three. So the first thing, I'm calling it the slit, but it doesn't always have to be a slit. But if you can imagine, from the telescope, you get an image that includes many different things. And if you try to get a spectrum of every single item in the image, things are going to overlap with each other. So the slit is something that most telescopes have in order to, or most spectrographs have, sorry, in order to focus you on one specific thing. So you can take the spectrum of one star in the slit and everything else is blacked out. That's why it's called a slit. Only one part of the light gets through. So whatever light you want to take the spectrum of, it goes through there, and then it gets to the prism or the dispersive element if we're trying to be very general about it, because it can be a prism or a grating or anything where when light comes in a certain angle, it'll leave at a different angle depending on its wavelength. Lenses or mirrors to refocus things back onto the camera to make a coherent image. And that's all you need for a spectrograph. So if you just wanted to build a spectrograph, you can go home now. But for what you actually get from this is the spectrum. And I'm showing here kind of two different extremes of what a spectrum can look like. The first one is a spectrum of a star, similar to the one that I showed of the sun. So that's a long wavelength range, and you see these absorption lines where specific molecules have absorbed the light at a particular wavelength. But there's also another type, so emission lines, meaning that those molecules can give off light at a particular wavelength. So you might have no light and then light at one wavelength. And you can also have spectrographs that will give a spectrum over the entire field of view. So this is what you're seeing in the one that's at the bottom there, is you're getting this tiny spectrum just around one line of an entire image instead of just one star in the image. Okay, so the spectrographs that I work on are all about observing galaxies. So I love talking about galaxies. You're sitting here, so you have to listen to me talk about galaxies. And the most fun part about galaxies, in my opinion, is called the circumgalactic medium. So this is not part of the galaxy itself. If you've seen a picture of a galaxy, you can imagine there's like the stars and the spiral arms. And then beyond it, there's some empty space around a galaxy before it gets to the next galaxy, right? But it doesn't just go from the galaxy itself to the empty space. There is this kind of cloud of gas that's in between, and that acts as this like middle ground between the galaxy and the empty space. And it interacts with the things outside of the galaxy and with the galaxy. And that's what I like to look at. It is very faint, so it's very difficult to detect. But as I tried to show by the rainbow of light coming out of the circumgalactic medium, it has many different molecules of many different temperatures. And so it gives off light at a bunch of different wavelengths. So we can look at it with a radio telescope and we'll see one thing. We can look at it with a UV telescope and we'll see something too. It's not a particular wavelength. So we can look at it in a bunch of different ways. And the instruments that I've used to observe what we call the CGM is one of them is on the ground, so it's called CHAS, and the other two are space instruments. Lioness is a satellite and Fireball is a balloon telescope. And I'll show you guys pictures of all of them. I just wanted to point out also, Fireball is a different color because that one is also a UV telescope. So the other two are optical. They're using light that's in our eyes' visible range. So this is a model of CHAS, and this is also kind of, when you're trying to make a spectrograph, this is the first step that you have to do. You build a mock-up like this. So this is a mechanical drawing, including everything that's going to be holding up the optics. So the first thing is the telescope is not in this picture because, and this is true for lots of ground telescopes, usually there is one large telescope and it'll actually have multiple spectrographs, and they kind of connect different spectrographs at different times, depending on what you want to do, like Legos. And so for Can you hear me? Okay, great. For Chaz, the telescope was already there. We didn't have to build that. So we just had to build a spectrograph to go along with the telescope. So it'll attach the telescope up there. And then the main thing is, it's all the same components. It's a little fancy, but there's still just the slit, which in this case, I put it in quotes because it's not really exactly a slit. It's kind of this array of lenses, but it's the same exact thing of just trying to make it so that particular parts of the image are used. And there's the slit, there's the dispersive element, which is the grading, and then there's the refocusing optics. Actually, that's just this whole giant gray part that's hanging off on the left. So same parts of the spectrograph. And the next one, lioness, is actually, thank you, hello, okay, we're back. Very similar to Chaz. The main difference here is that lioness is a satellite feet long and 4 feet high. So it's pretty big. And lioness, this goes in a shoebox, but it's very similar. It has the same type of slit where it uses this array of lenses, and it actually has a similar bandpass and or like range of light that it looks at and field of view that it looks at. But it's just that because we're trying to make something that will fit in a shoebox, the design ends up being different. And these are the types of things that we have to think about a little bit when we're building an instrument. And the next one, Fireball, is actually kind of quite different. So like Lioness, it's not on the ground, so it needs its own telescope. So the first part is the telescope, and then the spectrograph is kind of, I showed both the optics model, so that's all of the mirrors, and the mechanical model here. You usually have to prepare both of those. But still our same basic components, right? So you have the slit. In this case, it's not an array of lenses. It really is a slit for looking at a particular part of the image, and the grading and the refocusing optics. So yeah, now you guys really can all go build a spectrograph. Now we get to the fun part, which is building it in the lab. I did skip over having to get money for your instrument, but that's not fun. So we're not going to talk about that. So I don't know if you guys notice. So for optical and for ultraviolet, we're both in the lab. It's similar things. We're gonna have to try to keep the mirrors in the correct places depending on our model and make it as similar to the design as possible. So those are the same. Is there anything in particular that you guys notice that's different between the two? And you can shout it out. Exactly. Yeah. For the ultraviolet one, we have to wear scrubs. I also, disclaimer, that is not me because I was not there for the ultraviolet one. But yeah, for the ultraviolet, you have to wear this crazy clean room attire. And you might think we had to wear masks for the optical one as well, but that's actually not to protect the optics. That's because it was 2020. So, so ultraviolet light, because it's a much shorter wavelength, really, really tiny microscopic particles can ruin the optics and make them not reflective to ultraviolet light anymore. So that's why you have to be super careful, not even to get, a single fiber or dust or anything onto the ultraviolet optics. Whereas the optical, I mean, you don't want to sneeze on it or something, but it's much more hardy, kind of. It's not gonna the efficiency won't go down by that much just from small things. So that's kind of the biggest difference in the experience of building them in the lab. And the next thing I'm going to talk about is testing them. Fireball. So for Fireball, this is a balloon telescope that it launches in the morning. It spends all day going up to the stratosphere. And then at sunset, it reaches the stratosphere. It observes for one night, and then it falls back down in the morning. It has a parachute though, so it's fine. But you really only get one night of data, whereas CHAZ is built to live at this observatory in Arizona, and it has stayed there for the past 5 years. So this was in 2020, as I mentioned. And it's been at the observatory in Arizona for 5 years now. So we've continued getting data from it. So they are very different. But I just want to show you what launching a balloon is like. So as you can see, Fireball is enormous. It's like the height of 5 people or something. And the way that they launch these is they have a truck that picks it up. That's this first image here. And then the train that connects to the balloon trails off all the way to the balloon. They start pumping the balloon filled with air, and then it starts rising up. That's the second picture. And when the balloon reaches exactly above the instrument, the truck lets go of it so that it can actually start to rise. And yeah, this is how they do all of the balloon launches. And in the third image, you can see it kind of starting to float away. So if it reminds you of Up, then I agree with you. But I just want to show you guys, this is one of my favorite pictures. It really goes very high up, so it looks like just almost like a speck in the clouds there. I don't know if you guys can notice, but it's a slight teardrop shape. If any of you guys were like, that's a teardrop shape, then you have a very sharp eye, because that kind of was a foreshadowing of what happened with our launch, which is there was a small hole in the balloon, so it didn't inflate as much as it was supposed to. And so the balloon wasn't actually able to reach the stratosphere. So we didn't get any data from this, but as Amanda mentioned, balloon flights are much cheaper than launching a space telescope, and that's kind of their thing. Like NASA's view on balloons is very much you try out new technology and it doesn't work sometimes, and that's how it goes. But luckily with CHAZ, it's not the same thing where you get one chance and one night of data and it's over. So I'll talk about that one next. Oh, so again, I just had to show the beautiful nature there. And since I showed pictures of the lab in New York and now I'm showing the telescope in Arizona, you might be thinking, like, how did we get this huge 4 foot by 8 foot spectrograph from the lab in New York out to Arizona? And the answer is me and another grad student drove it there. So Chaz is in this picture in the back of that van. We had to drive very carefully. um, but yeah, that was in 2021. And since then, we've had so many observing nights there. And the nice thing about an instrument like Chaz on the ground is that you really can go back and keep improving it. So over the past 5 years, we've made a bunch of small upgrades to it, and it performs much better now than it did in 2021. But this first picture is from the first run where we were kind of building it. We got several days to build it. So you can see, like, it's not quite closed. You can see a bit of the mirrors. And then the second one is from a few years later. So now it's closed. And we also got that little stuffed animal that's sitting on the top, which is the Chaz mascot. Her name is Jasmine, and she's a ring-tailed cat. Yeah, so we've had the opportunity to take lots of data with Chaz. It's been amazing. And I have spent over my PhD, I think I counted it up recently, and it was like 150 nights of my life observing at this telescope now. So I have spent many nights with this schedule, but I thought I would just share the observing schedule with you guys. You know, you have to stay up all night because that's when you can see the stars, or the galaxies in this case. So usually we wake up around 12 to 2 p.m. I will admit, sometimes I sleep in a little bit, but you have to watch the sunset. It's mandatory. So the telescope is very much in nature. It's an hour outside of Tucson, and they try to get it away from light pollution as much as possible. And so it's really just gorgeous desert scenery. So we always watch the sunset. And overnight, this is the telescope that Chaz is on, but you can't see Chaz in the picture because it's kind of behind that arm that's holding up the telescope. But overnight, we operate this telescope, and the nights are very different depending on whether it's winter or summer, but usually we'll just try to observe one galaxy for several hours to get kind of like a long exposure of several hours on one thing and then move to the next thing. Yeah, and then we go to bed 4 to 6 a.m. depending on the time of year. So in the winter, it ends up being really long work days, and in the summer, it's really short. So it's nice. And after doing this many, many times, you get some data like this. So Chaz is the type that I was talking about. These are a couple of my favorite targets. The first one is to interact in galaxies. There's that edge-on galaxy and the other spiral galaxy that's going to merge with it. So that one's very cool. And there's also the pillars of creation. So that's this area with lots of stars forming and clouds of dust and gas. So yeah, really happy that we've been able to get all of this data. And I wanted to finish off by thanking the animal friends, my cat Ruby, who helped me with the optics modeling, and my friend Nicole, who was in the photos with me. Her dog Banjo also visited the Fireball lab, so that was very fun. And of course, thank you all for coming and listening. And yeah, please let me know if you have any questions. Oh, sorry, I think Amanda is in charge of the questions.
Yes, I am in charge of the questions. Magna's right. So you are welcome to ask them out loud, or you can submit them on our form and I will be checking it. But I'll start with you. Yeah, so when you're done collecting data, how do you get the instruments and telescopes back from the balloon?
That is a great question. And I just learned it during the launch and it's amazing. But basically what you do, okay, so the balloon launches and then at some point, because it's a balloon, it will have no air left in it and it'll start falling. So it has a parachute and so it'll land pretty softly. So that will save it. But then the way that we get it back is that number one, there's like this crazy NASA wind model that like places it within some couple square mile radius. And the other thing is someone gets to go and I really wanted to go, but I'm only a grad student, so they didn't let me. But next time. Go ahead.
What instrument was Chaz attached to?
So what telescope did you hook Chaz up to in Arizona?
So the telescope in Arizona, it's a 2.4-meter primary mirror telescope, the Hiltner telescope. It's at MDM Observatory. So it's the same one that I showed in that like day in the life of an observer image. But so Chaz is in that picture, but it's kind of blocked. But yeah.
All right, we've got a question in the back. If someone were to hypothetically, of course, go on the balloon, would they survive that ride?
This is actually crazy because when I was there, I had a dream about being selected to be the balloon sacrifice to go up on the balloon. No, but sadly, no. The stratosphere is very high and there is no air there. It's basically a vacuum. So you would not survive. But if there's any interest in being a balloon sacrifice, that's fine.
Okay, there was another question back row. How big is the balloon that they use for Fireball, and what is the balloon material made of?
Oh, okay. For both of those, I wish I had like a more specific answer to give you. But for the size of the balloon, it's huge. So the number that I always remember is that apparently it's about the size of a football field is the length of the balloon. So yeah, huge balloon. And also for the material, I'm sure that there's some NASA scientists who's like spent their whole life coming up with this specific material, but it was to me very reminiscent of like clear garbage bag material. So like it's very thin and very light, and like I wasn't surprised that there was a hole in the balloon because it seems insane that like a football field sized thing of this material could not have a hole in it. But yeah.
Okay, let's see. You So, question about the Chandra Observatory in space. Do you know if it's being defunded or shut down?
I'm actually not sure. I know that there at X-rays again. So at least there's that.
I'm gonna take a question online. What instrument do you want to build next?
Ooh, okay, that's a good one. So okay, I really want to work on two things. I mentioned polarimetry, so I think that's very cool. I would love to work on a polarimeter next and understand more about magnetic fields in our galaxy. And the other thing is my next project that I'm hoping to work on is a proposed satellite telescope for looking at the UV. So not a balloon anymore. We're done with the holes in the balloon. We're going to satellites. But yeah, we'll see if it works out.
Question here. What type of telescope is the hardest to make?
Ooh, that's a really good question. I think bigger telescopes are much harder to make. So if you hear about like the 30-meter telescope or something, like those enormous telescopes, it just is difficult to make something that like is that big and can have a specific shape like it needs to have in order to focus light. So I think that's the answer that I'm gonna go with off the top of my head.
So the observatory.
Yeah, so you pointed out that it wasn't the telescope on the roof of Pupin. So if we're not using Columbia's telescopes, how do you do that negotiation to put your instrument on another institution's telescope?
So the Columbia has a share in MDM Observatory. It's kind of like a timeshare, actually. So everyone applies, and then every institution gets a certain number of days. And there's someone who decides, like, oh, the Columbia people are allowed to go on these days, and then that's when we're allowed to test out things with Chaz. But yeah, I know we have to, like a timeshare, we have to pay a certain amount to continue being part of the observatory every year.
So when you were building Chaz, did you and your teammates have different specializations that you were focused on when building the instrument?
This is going to be such an annoying answer, but yes and no, because some things we did all have to work on together because I don't know, when you're building things like there are some things that you need two people to do when you're physically putting together like putting the mirror into the correct place. You need two people to be able to fully understand what you're doing. And I would say the things that ended up being broken up were more of like the modeling and data analysis coding side of things. It ends up being like everyone specializes and people have specific projects.
Yeah, is Chaz now permanently on that telescope, or will it one day be removed?
So there are 2 spectrographs at the observatory and then 3 different just cameras, and they're like Legos. They just attach whenever you want to use Chaz, you can put Chaz on and use it, and then yeah, you can switch.
Another question online. What is the cost to build each of these instruments?
Ooh. I definitely should know this, but I think for Fireball, I would say the order of millions of dollars. For Chaz, I think it was about 200,000 or something dollars. And I think Lioness was the cheapest, but the number is escaping me right now. But yeah.
Okay, I'm going to take one more question online. Magna, when you showed the images from discs.
So those are stars. Sorry, I'm gonna go back if you don't mind. But yeah, so as I mentioned, that there's a very short wavelength range, and most things that we're trying to look at in galaxies just give off light at a very specific wavelength. So that's what creates the dots in the image. But the streaks are stars because stars give off light, as we could see from the sun spectrum, they give off light at a bunch of different wavelengths. So they fill the entire wavelength range, and that's why they look like streaks in our image as opposed to just dots at one wavelength.
Awesome. And there is an announcement. Someone looked up at savechandra.org. It does seem like Chandra is safe for now, so not being defunded.
Perfect.
Okay, so let's give another round of applause to our fantastic speaker, Magna. Thank you. All right, before you go, we don't have observing for you, but we do have a raffle for you. So on the back of your seat, there is a letter and number. This is usually how folks figure out where they need to sit for some scary physics exam. We like to use it for